Good morning, or good afternoon, or good evening, or whenever you are watching this presentation. My name is Rose McGroarty, and I am a graduate teaching assistant with the Department of Geosciences at Virginia Tech. And I'm going to be presenting to you about teaching students to love learning geology online. Just a little bit about me. I'm a second year master's student at Virginia Tech, as I said. I actually got my bachelor's of science in geology at James Madison University in 2017. Currently, I am researching the thermal evolution and lithospheric composition of Mars, which is funded by the Virginia Space Grant Consortium. I am a GTA, which is graduate teaching assistant for Geoscience 2104 Elements of Geology. This is an introductory geology course that is designed for engineering majors. And this semester, because of the pandemic, we are teaching this class completely online. This is my fourth year as a teaching assistant. I've been a teaching assistant for 2 years at Virginia Tech. This is my second year. And I was also a teaching assistant for 2 years at JMU in undergrad. So before I talk about teaching geology online, I want to focus on why it's so important to teach geology in high school, because I truly believe that we need to be teaching geology in high school and in middle school and in elementary school, and read it to your babies. Geology is a really wonderful science. It's a very broad science, and there are a lot of careers that you can focus on in geology. And these can include researchers, which is my chosen profession. You can also be a soil specialist and work out in the field studying soil. You can be a hazard assessor, so you can study landslide potential or groundwater contamination, which is connected to water scientists as well. All of these people and more can be engineering consultants working for engineers and with engineers to give them guidance for projects, particularly in the civil engineering field, but in others as well. Natural resources, these typically include mining, but they could include other things. And of course, energy, which is a very big industry right now with oil, natural gas, and clean energy. And we have a huge need for young geoscientists. Geology is a very low diversity science, unfortunately. We have a low percentage of minority students and minority professionals, and we have a low percentage of women in geology. Most geology majors actually change to a geology major after starting college. So they come into college undecided, or they come in as some other major, maybe in science or engineering or math or maybe something else. And they take a geology class and they realize that they want to major in geology. But most of them do not come in to the university as a declared geology major. And so we have a desperate need for high schoolers and middle schoolers to gain interest in geology. We need to diversify our field, and we have job opportunities that need to be filled. And the more people we have in geology and just interested in geoscience, the more our science and society will be enriched. So geoscience is typically taught in the eighth or ninth grade. And unfortunately, and this breaks my heart, there are students who actually report that they consider geology a soft science option. And so there really is this need to reach students about geology as a career and as a field of study and as something that you can major in college and then go on to graduate school. There is difficulty in engaging high schoolers, and I think this may be a problem across high schoolers sometimes. And that's really a pity because geology is a very interesting science. It's very interesting and it's very broad. If you're interested in planets, you can study geology. If you're interested in rivers, you can study geology. There are so many things you can study geology to do. And I think it'd just be wonderful to get more high schoolers to understand all the opportunities that are open to them in this field. Unfortunately, online instruction does make both teaching and learning geology more challenging, which is why I want to talk to you about some of the methods that we are using at Virginia Tech to try and make this geology instruction a little bit easier for the students and help engage them in the science. And so the problem, get right to the point, geology is a difficult science to teach online. And that's partially due to the nature of the science. It requires hands-on experience. I like to say geology is about so much more than learning about rocks, but it really does come down to knowing rocks, and it's very hard to teach those in person. Oh, excuse me, online when you're not in person. We need physical samples, we need in-person observations. If I hold up this sample of feldspar to the camera, it just isn't the same as being able to pick it up yourself. There are tools that we can use to help students connect. And thankfully, there is more to learning geology at the introductory level than learning rocks. And so there are other things that maybe we can enrich our classrooms in addition to the rocks and minerals, to help bring other things into the classroom and help the students get a little bit of an easier experience learning online. And so some of the tools that I like to use are Google Earth and Google Cardboard. And I will talk about those in a moment, but I also want to talk about ways to encourage student success in the classroom, particularly in an online classroom. And I know that this audience here, you are a teacher and you know how to encourage student success. But these are some things that I've found have really helped me teaching students geology. And so one thing that I like to focus on is giving the students relatable goals. So I tell them professionally, and of course I'm speaking to engineers right now, I say, I want to prepare you for later courses and I want to prepare you for your career. I'm speaking to civil engineers and I tell them, I want you to have an understanding for the rocks. I want you to have an understanding for hazards in this area where you might be building. And I want you to know when to call in an expert to give you some consultation. When I'm speaking to geologists, I tell you, I want to prepare you for future courses. I want to prepare you for your career. But I also give them a personal goal. I want you to better appreciate the natural world. One of what I think is one of the most amazing things about geology is that it teaches you so much about the world around you. And when I go driving through Western Virginia or West Virginia, I can pull over at almost any outcrop, really any outcrop, and I can say, I know how these rocks were formed. I know what type of rocks are here. I know what environment they form in. I can tell you with maybe 98, 99% certainty that these rocks here came from an ancient river. And I think that's a pretty cool thing. And I really want my students to get a little bit of that. Of course, in an introductory course, we can't expect them to have a higher level understanding, but to have an appreciation and to be able to recognize things in the world around them is really a very powerful skill for any person to have, I think. And I also want to present career opportunities in geoscience because there are so many career opportunities. And many people, I think, don't realize that there are so many jobs available in geoscience. Another tip, this is a general tip from teaching that I have found helpful, but this is also, I think, really, really very important for me teaching online, is to be flexible. Geology is an innate skill for some people, but it's not so easy for others. And so some people, they just pick up geology right away, and others, it's not so, it's more extrinsic. They need more time, they need to study more. And I found that students tend to do well with rocks and minerals or with the maps and theories. And it's kind of funny because they do very well the first part with rocks and minerals, and then they don't do so well the second half, or vice versa. And I'm not entirely sure why that is, but it is something that I have noticed. And that is something that I try to keep in mind with the students, whether encouraging them or also keeping in mind that I may need to help them more later in the semester. Learning geology online is even more challenging. And so I have been very flexible with my students and really trying to work with them. And I have found that given a little bit more time and effort on my part, they are learning just as effectively as they have been learning in the previous semesters where we were online. And this is great life advice, I guess. But for me, geology is the most exciting thing they will ever study. And I've found that the more passionate I am about geology, the more passionate they are. So eat, sleep, and breathe geology, and they will too. So moving on to some tools that we can use for teaching geology online. Google Earth is a very powerful tool. It has the benefit of being free. And we can use this to prepare virtual field trips for the students. And what's really beneficial about this is that these field trips do not have to be live. We can pre-record a file and we can set up field trip stops along different points in an outcrop. And we can say, I want you to go to stop one, and they can click on stop one and they can read the information and they can see the outcrop in Google Earth, which is a very powerful tool for them when they're not able to go somewhere. We can also use overlays, and these can include geologic and topographic maps. They also include soil maps, and these give them a tremendous amount of information about the geology of a place, any place. I know, and I've actually included the links to get the geologic, topographic, and soil maps for the entire United States. Unfortunately, I have not tracked down maps for the for global maps, but I am working on it. And as I mentioned, this is very suitable for independent work because you can give them these files and you can give them the assignment and you can say, have at it and let me know if you have any questions. Another note about Google Earth: you can download Google Earth on your computer. You can also open it in a web version, and there is an app for the phone. I do not know if you can use these virtual field trips on the phone, but I know that you can use them in both the web version and the app version on the computer. Now, Google Cardboard, and this is one that I think people laugh at a little bit. It's a Google Cardboard device, but this is a very interesting virtual reality experience. And the app for it is free. Students can either buy for maybe about $10, or maybe the school can buy for $10, or the students can make their own cardboard at home. And this gives them a virtual reality experience where they can actually go to, say, Mount Everest, and they can actually have the appearance of hiking up Mount Everest and looking around them 360. And that's a really powerful tool that we can use. It's a little bit more suitable for guided activities and guided field trips than it is for pre-recorded, because you can actually, as a teacher, have an app where you say, I'm going to tap on the app right here, and it directs everybody's attention to a particular feature. They all start swiveling around with their heads in the virtual reality, and then they focus in on that spot that you've indicated, and then you can talk about it. So some sample activities that I'm going to go over, and I wish I could go over every activity that we're doing in our lab right now, but I did select 3 activities: the Plate Tectonics Lab, the Geologic Time Lab, and the Geologic and Topographic Maps Lab. I'm also going to talk about the final project that I'm assigning to my students. And then I will also include a brief note about teaching rocks and minerals, because even though that's not the focus of my presentation, I did pick up some helpful hints as I was doing that this past semester. So plate tectonics. This is a lab that helps students explore how the Earth's plates move. And it helps them understand different plate boundaries and the risks and hazards associated with these plate boundaries. And of course, what you're teaching, you may change the focus of the lab a little bit. We focus heavily on risks and hazards because we're teaching engineers who are building along these boundaries. So why it works: there's easy access. We can use Google Earth, a web version of Google Earth, or there's a website with the same interactive map as Google Earth. So if a student maybe doesn't have access to Google Earth for some reason, although I think they should because of the web browser version, even if they can't download it, there is the website with its interactive map. We could also, if necessary, print a map for a student to either mail or arrange for the student to pick up. We use rates of motion for the plates, and these are available free from NASA, and they can be printed for students without reliable internet access. And it gives students this practical, hands-on application of plate motion, and I think it really helps them understand how plates are moving and what types of plate boundaries we have and what hazards and risks are associated along them. And we can make it as basic or as challenging as necessary. This is a very easy lab to make a little bit easier or make a little bit more challenging depending on what the students need. So the activity overview: we view the earthquakes on an interactive map, and I actually want to add a quick note and say that these resources, these rates of motion from NASA and everything, they are available on a PDF, which I do have accompanying this presentation. So we can view these earthquakes on an interactive map, and we can have the students start off by saying, well, look at where these earthquakes are located. And now why don't you tell me, what do you think that means about the plate boundaries? And then the students can toggle on the plate boundary map, and they can compare the global distribution of geologic hazards to the plate boundaries. So they can notice the distribution of earthquakes, and they can notice that they are more common along convergent and transform boundaries. And they can also notice things like finding volcanoes along divergent and convergent plate boundaries. And then tracking plate motions, I think this is a very exciting activity. This is the sort of activity that I just do for fun. You can actually find the rate of change in latitude and longitude. This is available free from NASA for thousands, hundreds, I don't even know how many GPS stations around the globe. And all of these GPS stations are tracking how the plate is moving, or how that particular station is moving, in both latitude and longitude. And so when you go on the site, you can just pull this number off of a plot, and it will even tell you rate, 3.1 millimeters per year, plus or minus some bit of error. And so you can pull off these rates of change. And I do want to make a note that the positive is for north or east, and negative is for south and west. So you won't see northwest, east, south on the actual plots, but they will give you a positive or negative, and that is your directional component. And you can use the Pythagorean theorem to solve for the rate of motion. So we know that a plate boundary is probably not moving due north and then straight over to the west. But what we do know is that the plate is moving northwest. And so what we can do is we can use the Pythagorean theorem to say if we have this amount of motion that's moving straight north, and then we have one that's moving over to the west, then we can use those, we can put them together, and we can solve for the hypotenuse of a right triangle. And so we use the Pythagorean theorem to solve for that rate of motion. And when we do that, that tells us that the plate is actually moving some distance to the northwest. We can then use trigonometric functions to solve for the azimuth. And there is a more detailed guide to how to do these activities on my document that I'm including with this presentation. But essentially what we do is we solve for a particular angle on the triangle. And that angle is between the hypotenuse and the north. And it does depend on how they set up the triangle. So I'm trying not to be too specific because there are a couple ways to do this mathematically and still get the correct answer. But when you solve for this particular angle, that will give you a sense of where this falls on the compass. And so what you need to do is then add or subtract from the cardinal directions. And then that will tell you the actual azimuth. If I were to pick up a compass and say, which direction is the plate moving? Then I would know, for example, this plate is moving at an azimuth of 350 degrees. And that would be all I would need. I would not need, west of northwest or anything, north of northwest, any sort of directions like that. And so what's really cool about this is that they learn how to actually calculate the plate motion and the azimuth that the plate is traveling at. So now these students don't just need to be told, well, just believe me, students, when I say that the Pacific plate is moving northwest. No, they can actually pick up a pencil and maybe a calculator. They shouldn't need it, but if they need it, that's whatever. They can pick up a pencil and a calculator and they can solve, and they can find how these plates are moving. And I think that's a pretty incredible thing for students when they realize that they can just take GPS data and get this type of information out of it. And so the next lab that I want to talk about is geologic time. And geologic time builds an appreciation for the time span of geologic history. Because geologic history, there's a fantastic graphic actually that talks about geologic history and human history. And if the entire world's history took place over 24 hours, then humans would not appear until the very last minute on that clock. And I think that's really incredible. And I think it's sometimes a little bit hard for us to grasp because we're not used to that type of time scale. I talk to my students, they're engineering majors, and I say, what's a long time to you? And they say, oh, 50 years. And I say, I would say 50 million years. So there is that disconnect between geology and what people usually think of as a long time span. And so what they learn in this lab is they learn how to use relative and absolute dating methods. And they get to practice using these methods in a variety of scenarios. So again, this is an easy access lab. This actually does not need to be done on the computer unless maybe you want to have them submitted online. And it builds on very easy to follow concepts. So I divide this activity into two segments. We have relative dating and we have absolute dating. And relative dating is based on the relationships of rocks and fossils to each other, while absolute dating is based on radioactive decay. And absolute dating is pretty precise, but we do need to keep in mind that there is some margin of error in the calculations. So relative dating is based on these laws right here. We have the law of superposition. We have the law of original horizontality, the law of cross-cutting relationships, and the law of conclusions. And I just make this note partially to myself to remind students not to get the latter two laws confused, because sometimes the law of cross-cutting relationships and the law of inclusions can get a little bit hairy if you're not sure if something is actually cross-cutting or if it's an inclusion. And of course, if you're watching this presentation, then doubtless you already are an earth science teacher or a geology teacher, so you are familiar with these laws. And the way I like to teach this is with puzzles, because everybody loves puzzles. I personally think that these puzzles are so much fun that they should be in the daily newspaper along with the crossword search and the word search and the Sudoku. And so we can deconstruct this geologic history by using the laws that are on this previous slide here. And when we do this, and I'll just go through this very briefly, we find that A is the first layer deposited, B is deposited on top of A. Disconformity K comes along, C is deposited on top of K, D deposited on top of C, and E deposited on top of D. E on top of D. Now we get a little bit confused. Which comes next, I or J? Well, we see that J stops in E and I continues up above E. So we're going to say that J happens after E. And after E, we have disconformity L. We have F, layer F deposited on top. We have layer G deposited on top of F, layer H. I is some sort of magmatic intrusion. And then we have M, which is some sort of erosional feature, which will eventually be a disconformity. So these types of puzzles are a lot of fun for students. I made this one up myself for my students. You can make them up, you can find them in places. Students like these puzzles. I like these puzzles. I think everyone likes these puzzles. And it's really a great way to teach students about these relative age dating laws. We can also use absolute dating to determine the ages of samples. And this uses radioactive decay to find the age of a sample. And this age does include error. And so we use this equation right here if we want a very precise answer. And this equation is very straightforward, and I'm sure you're familiar with it. It just is that the half-life of the radioactive element divided by the natural log of 2. You take that quantity, you multiply it to the natural log of d over p. This is the daughter product divided by the parent product plus 1. And so just a quick reminder, I'm sure you know this already if you're watching this presentation, the parent element is the radioactive element that decays, and the daughter element is the element that the parent decays into. It's the stable element, or stable isotope, I should say. There is an easier way to do this, but it is a little bit more approximate. And what you can do is you can determine approximately how many half-lives have elapsed. And then you can multiply that number by the duration of the half-life. So for example, if we have a sample, and I won't go through all these examples, but if we have a sample that contains 12.5% uranium-238, well, I know that the half-life of uranium-238 is 4.5 billion years old. 4.5 billion years, excuse me. And so when I want to solve this sample, I can go back and I can put the numbers into this equation here, or I can approximate it. And I can say that after one half-life, I will have 50% parent and 50% daughter. After a second half-life, I will have 25% parent and 75% daughter. After a third half-life, I will have 12.5% parent. And so right here, 12.5% uranium-238, that's the parent element. So that tells me that 3 half-lives have elapsed. I can multiply 3 half-lives by the half-life duration of 4.5 billion years, and that gives me an age of the sample of 13.4 billion years. Pretty straightforward. It is, however, more approximate. Now, when I say more approximate, if you look at this next sample, which contains 70.7% uranium-235, this is less than 1 half-life's worth. It's about half of a half-life. It's about half of a half-life, which means that it's approximate. And I do want to emphasize about half. So you can say, okay, I'm going to approximate this sample, and I'm going to say that this is 1/2 of a half-life. And considering that the half-life of uranium-235 is 703.8 million years, it's probably okay to make that approximation. However, if you want a more precise calculation, it would be better to plug in these numbers into this equation right here. And then this is just a thought question that I like to give to my students because I think it really gets them thinking about how we use relative and absolute dating together. So let's just assume that a beach is made up of zircon crystals. And you take these crystals to your lab and you determine that they are about 500 million years old. How old is the beach? And so here's where I have students, and a lot of times they're thinking very critically and very well about, well, the zircon crystals are on top of the beach, which means the beach is older than the zircon crystals. And that's a reasonable way of thinking if you're thinking about the law of superposition. So the assumption that I'm making is that the beach is made entirely of these zircon crystals. The other thing that I'm thinking, that I am assuming, and that I want them to think of, is that the zircon crystals did not form at this beach. So we are not assuming that the zircon crystals formed at the beach and that or formed in an igneous rock and then weathered into the beach on top of it. We are assuming that these zircon crystals formed some distance away from the beach in an igneous intrusion, which is how zircon crystals form. They were weathered down, eroded, transported to the beach, and deposited and formed the beach. We're also assuming that the beach was not there before the zircon crystals were deposited, that the beach started being a beach at the same time the crystals started being deposited. These are just assumptions that I make because my students kind of overthink sometimes. They're great. So if we make these assumptions, we find out that the beach is less than 500 million years old. And sometimes it's a little bit hard for them to understand why this is the case. And so what I like to ask them is, how old are you? And of course, I teach college, so my students are usually between 18 and 20, 21 years old. And I say, how old are you? And the student says, 19. I say, okay, Johnny Appleseed, you're 19 years old. Does that tell me how long you've been sitting in the room you're sitting in now? And of course, Johnny Appleseed thinks it through and says, no. I say, that's right. But it does tell me that you have been sitting in this room for less than 18 years. And that's when they start to realize, oh, I see. The zircon crystals were born 500 million years ago in an igneous intrusion. They didn't just weather down and form a beach on top of that intrusion. They weathered down, they were transported, deposited on the beach. And now this beach is younger than 500 million years old. How much younger, we don't know, but we do know that it is younger. And then finally, the last activity that I'm going to go over, which is very sad to me because I really want to go over all of them, geologic and topographic maps. And I think this is a very important lab because, especially if the students are not able to learn how to identify the samples in person as well, this is a very important lab for teaching them about the impact that these rocks have on an area. And so the students in this lab, they gain experience reading topography off of a map, and they learn about rock relationships as they're seen on the surface. And what I mean by that is, if I'm walking across town and I can see that there's this type of rock here, maybe a limestone, and maybe there's a sandstone right here. If I'm looking at a map, then I will see limestone, sandstone, and they will be in contact with each other. And so they can get a sense of those relationships from looking at this map. It also gets them to start thinking about how rocks and topography affect groundwater flow, landslides, and other hazards. So why this works? These map overlays are available for Google Earth, and they can be used in both the downloaded and web versions. And as I said before, I am not sure if they can be used on the app on the phone. All of these materials are free. Google Earth is free, whether it's the app or the web version, and these map overlays are free. It also is possible to print the map if a student needs it because the student does not have internet, and then maybe get the map to the student somehow. And students learn the relationships between rocks and topography. So they learn, for example, that harder rocks erode very slowly and they form ridges, whereas softer rocks erode more quickly and they form valleys. This is just one example of that relationship between rocks and topography. This is what the topographic map looks like in Google Earth. It looks like a regular topographic map. This could be a topographic map that I bought from a survey company. And it's very nice because being Google Earth, I can scroll in as much as I want. I can scroll out. I can adjust the scale. And that is actually a very nice feature in the Google Earth overlay. And so just some quick examples of what some of the questions that I ask for this lab. I asked them to find things such as the stream water flow, the direction of it. So I might say there's a river that's flowing down the northwest side of this particular mountain. Um, I should rephrase that question. I give away the answer. There's a mountain, there's a stream flowing in the northwest corner of the map. Which direction is it flowing? And maybe the stream is flowing northwest, or maybe it's flowing southeast, or maybe north, whatever it is. They would need to use the topography, and they would need to use the features of the map to identify the direction that the stream is flowing. This has an impact on hazards such as landslides and an impact on hazards such as groundwater contamination. If a student spills Coke on the top of a mountain, that Coke is going to get into the groundwater and it's going to go somewhere. Or even more disastrously, if they spill motor oil, then that will get into the groundwater. And so I guess I'm thinking about what impact does contamination have downstream and where will this contamination go, which is very important when you're teaching civil engineers, and I think also teaching anybody, because we should all be aware of the impact that we have on the world around us. It can also give them an idea of the age relationships of rocks using a geologic map. And so if we accompany this with a list of the rock formations of Virginia, and I just use Virginia because it's convenient because I'm in Virginia, then we can have them identify the rocks based on their age relationships. And then they can identify geologic structures. They can identify synclines and anticlines without actually looking at the rocks, because they can tell if the oldest rocks are in the middle of the structure or in the outside of the structure. And that's really a very powerful thing to think, that you can be walking across a flat surface and know which way the rocks are dipping, which way they're tilted under the ground, just based on the age relationship between that rock and the rock next to it. And I think that's a really powerful thing that I really try to teach them about. They can also identify faults on the geologic maps, and they can also get a sense of possible hazards such as landslides, erosion, or even earthquakes. And so very quickly, I want to give an example of a final project that I'm using this semester. And this is to replace the final exam that we usually give them in the lab, because a final exam is good for some things, but I think for a lab, there are better ways to really incorporate these concepts and get a sense of how well they understand and can apply what they've been learning in the semester or in the school year if you're teaching in the school system. I keep thinking college. So this final project is a report for the geology of a particular area. And because this is for engineers, we give them a particular assignment. So say, for example, a nuclear power plant along the San Andreas Fault. And it is the student's job to look at the rocks and the topography, the groundwater flow, the soil, and look at the local hazards, flooding, earthquakes, volcanoes, the impact of climate change. Is it along a shoreline and the sea level is going to rise? Or will this project have an impact on the climate? And then they make an assessment whether or not they would approve that project. And this semester, we are having them submit it as a group paper, but there was some debate as to whether it should be a group paper or a group presentation. I think either could work as well. And then just very briefly, a note about rocks and minerals, because even though I'm not talking about rocks and minerals as a primary point of this presentation, there are some tips that I learned that I thought that I would share. So rocks and minerals are the most difficult thing to teach online. They are why geology is difficult to teach online. Everything else we can use in Google Earth, and we can pull resources, and maybe in some ways it's even enriched because they have virtual access to so many places around the world. But rocks and minerals are hard. And so they are also very vital to understanding geology, and so we can't leave them out. What we did this past semester was we actually gave students their own samples to take home. We have the privilege of being able to charge lab fees for our students, and so we can use those lab fees to purchase samples and give samples to the students. But we also took pictures and videos of the samples that we normally use in the lab. And so these are regular pictures. We also took videos of, say, scratching a mineral against glass, or putting a little bit of hydrochloric acid on a piece of calcite. I took a great video, and I will share the link as well, of smashing a couple of samples to get an idea of the cleavage planes in the mineral. And so there are all of these different techniques that we can use by using pictures and videos. And really, the big takeaway that we had from this was to be patient with them and to understand that understanding is more important than answering. It's more important to me that my students understand why calcite reacts with hydrochloric acid than to see that sample 3 reacts with hydrochloric acid. And so this is maybe something where we've needed to change our technique a little bit and focus less on, did you recognize that sample 5 scratches glass? Or do you understand that sample 5 scratches glass because it is harder than the glass? And so changing our expectations for the rocks and minerals have actually really helped us to teach the students more effectively and get better results from their learning, because even though they may not necessarily be able to look at a picture of the sample and identify it, they understand why samples have the properties that they do. And so I'd like to conclude. I'd just like to give some feedback from some of my students. So I asked my students this past weekend, actually, if they would mind sharing a little bit of feedback anonymously. And so one of my students said, I'm an international student and I've learned about plate tectonics. I've learned about how they are very important in history of the earth and their importance when analyzing how they are related to the different rocks and minerals on earth. I learned how the different types of plate boundaries and their displacements cause different seismic movements of different ranges. Another student said, after completion of the mineral and rock labs, I was able to apply what I learned and successfully identify rocks and minerals on hiking trails that I would have not been able to identify otherwise. This is my favorite review because I thought, yes, you can apply this, you know this. This is something that's interesting to you. It's just in your everyday life. Goes back to appreciation for geology. This made me so happy. And then another student said, even with geology being online, the lab helped a lot to learn to apply the knowledge rather than just taking notes on topics. I definitely understood minerals better after the lab, and I enjoyed the lab very much. And so I was very happy to see this feedback because it tells me that what we're doing so far has been effective for the students, even though they're not in person with us. We are giving them these at-home resources. We're utilizing Google Earth. We're utilizing various other resources from the United States Geological Survey in the way of maps, overlays. We're sending samples home with them. We're providing these videos. And so even though they're doing this on a computer or on pencil and paper, they're still applying what they're learning and they're still getting a better understanding of geology and an appreciation for geology in the world around them. And so, in conclusion, teaching geology online has challenges. And I'm not going to pretend it doesn't have challenges, but it is very rewarding. And these interactive labs really do make the learning enjoyable. I wrote these labs, based on some previous existing labs, and I really enjoy teaching these labs. And I think the students really, based on their feedback, are really enjoying these labs too. Um, the projects and assignments, when we make them relatable to the students, it really helps them internalize the material. And even if the only thing they ever take from this class is, wow, I recognize this rock on the hiking trail, hopefully the engineers have a little bit more that they take away from this class. But even if your students, even if my general students who are not engineering majors and who don't need this for their careers, even if this is just general education science for them, if it helps them understand the world around them better, then I'm going to call that a success, because ultimately that's what I want for them to get from it. And I think that it's really amazing that even in this online platform, we can use these resources to give that to them. If anybody would like to reach out to me, I am going to put my email address in the document with the PDFs. I'm making a PDF document with all of these links and resources that are accompanying this presentation. And so if you want to reach out to me and ask me any questions, I'm more than happy to talk to you anytime. Thank you very much. Bye.